Hello everyone, I'm Kanghyun from UC Berkeley. Today, I'm going to present our work on integrating predictive motion uncertainties with distributionally robust risk-aware control for safe robot navigation in crowds. Today, we want to extend our robotics application to unstructured everyday life. This would include autonomous vehicles and service robots that we can see in our daily life. Key points in this transition is that human and robot will share same physical spaces. In this shared space, ensuring the safety of human-robot interaction is necessary. Therefore, our work focuses on safe crowd navigation, which guarantees safety within complicated and random motions of multiple humans. In the crowd navigation, there are two main approaches. First, reinforcement learning approach that tries to learn policy using end-to-end fashion usually have advantage of efficiency in process execution after it is trained. Also, they can integrate complex human-robot interaction behavior in their deep neural network models. However, their main disadvantage is that their lack of interpretability and guarantee for safety constraints. The other is modular approach where we divide prediction and control problem. This has benefit of interpretability and changing robot behavior by modifying control parameter. However, it might suffer with error propagation stemming from trajectory prediction and computation burden for constraint optimization problem. In this problem, we chose to use modular approach to give interpretable risk analysis and safety guarantee while addressing its drawbacks. When taking modular approach, we can benefit from machine learning-based trajectory predictors. These trajectory predictors have shown great performance with recent developments in generative models. However, there are still some challenges in using this prediction for safe navigation. First, human trajectories are stochastic and multimodal in nature, and generative model tends to give finite sample trajectories rather than full distribution of trajectories. In addition, due to complex and interactive behavior of pedestrians, true trajectory might shift from their estimation. Based on these challenges, we conclude two key points in our contribution. First, we give interpretable and tractable risk measure when only finite samples of future trajectory is given by generative trajectory predictor. Second, our risk-aware planning is robust to prediction error that can stem from machine-learned trajectory forecaster. First, we can start with how we measure risk when there is uncertainty in the human trajectory. In this work, we use chance constraint because collision probability is most intuitive risk measure for navigation task. However, chance constraint have a problem of being non-convex, which makes it computationally intractable. Moreover, if one tries to approximate chance constraint, it usually requires a large number of samples to give approximation guarantee. To overcome this problem, we use distributionally robust chance constraint, which enables to evaluate constraints with limited information about the distribution. In distributionally robust constraint, we want to satisfy constraint not only for sample distribution, but also for all distribution in ambiguity set. In this work, we use ambiguity set that shares mean and covariance with sampled trajectories. Using distributionally robust approach have two benefits. First, we can get tractable approximation of chance constraint without the full PDF and only with limited information, which is first and second moment in this case. Second, we can have robustness for distribution shift of true trajectory from prediction. Therefore, we can conclude that this distributionally robust chance constraint can act as interpretable and tractable risk measure while being robust to distribution shift in motion prediction. To verify our method, we introduce simulation setting with real-world pedestrian dataset and state-of-the-art trajectory prediction module. We use Trajectory++ as pedestrian trajectory forecaster with ETH hotel pedestrian dataset. Based on the prediction, we solve constraint control problem using cross-entropy method. To enable real-time performance in sampling-based optimization, we use GPU parallel computing. We compare our risk-aware controller with baseline, which use deterministic trajectory prediction. We can observe that the baseline do not yield to pedestrians coming from the left and then collide with them. On the contrary, when our method notices incoming pedestrians, it decides to wait until they passes to avoid collision. This behavior shows that accounting for uncertainty is necessary for safe crowd navigation. We also found intuitive but interesting behavior that collision probability balances between safety and efficiency. We tested our method with different collision probability, and for lower collision probability, the robot is willing to take longer detour to maintain larger human-robot distance. This monotone relationship shows that our method can give intuitive risk evaluation. As a conclusion, we address safe crowd navigation problem using risk-aware control, accounting uncertainty in human trajectory forecasting. We use distributionally robust chance constraint to give interpretable and tractable risk measure for multimodal uncertainty from human trajectories. Finally, we show that risk analysis is essential for safe crowd navigation, and our collision probability can balance the trade-off between safety and efficiency. That's the end of our presentation, and I would like to thank you all for your attention.